Okay, hello physics students. This is going to be the second video from chapter 8. I'm going to come back and do example 812 in another video, so there'll be 3 videos of mine for chapter 8. So in this example, this is going to be like a really fundamental one, definitely one you want to know. We're looking at a sphere that's rolling, rolling, so it creates this epicycloid type thing as it goes down the hill. And we want to think about that, and we'll also want to compare that to problems on inclined planes that we did before, where we just thought of just like a frictionless box, or a box sliding down an incline on a frictionless surface, okay? So now we're also, since this thing is rolling, we're going to have to do a rotational part to this energy problem, okay? So first, I think, what is the question they ask? In this question, I think they ask, what will the speed be when it reaches the bottom? So I think that we want the final velocity. Let's write that down. We should always do that as part of our problem-solving process. Get freaking thin line. Okay, there we go. All right, so we're going to apply conservation of energy. The energy of the ball at the top of this should equal the energy of the ball at the bottom. A couple assumptions that we're building in is that there's no slippage. Friction would basically cause the ball to slip and make this problem a lot more difficult, so we're pretty much ignoring friction just like we ignored friction for a lot of other situations, okay? So we're going to apply conservation of energy to the system that starts at the top, ends at the bottom. And okay, so what is the energy at the top and the bottom? So we've got the same old kinetic energy just due to linear velocity of the ball moving down. We've also got the potential energy at both points in the system due to the height. Just this is the gravitational potential energy. And here now, since this ball is revolving or rotating, now we've also got a rotational kinetic energy, which is just basically what we discussed in analogy in the first film. So instead of half mass times velocity squared, we've got half and the rotational equivalent of mass, if you remember, and sorry, my thing's like freaking out there. The rotational equivalent of mass is called inertia, so we create the inertia for the center of mass for that particular kind of object. Our object, of course, is a solid ball. It's going to depend on what kind of object you have. So at this point, I'd like to highly recommend that you go and watch the calculus derivations of a couple of those other objects. So on page, what was it in the book? Page, let me see, flip back a few. Page 208, it has basically the formulas for the center of the inertia for a variety of different objects, okay? But anyway, now we've got this also kinetic energy term, which is half rotational mass, rotational velocity, okay? So that's going to add some extra kinetic energy, which makes sense. I mean, if it's revolving, I mean, it's going to get some extra energy that's in motion, all right? So I think at the top of the hill, its velocity is 0 because it hasn't started yet. Its rotational velocity is also 0 because it hasn't started yet. And its potential energy is its mass times gravity times the height that we start at on the plane. So height, yep. Okay, then once we get to the bottom, point 2, I think its regular kinetic energy has now acquired its final velocity part. Its rotational kinetic energy is whatever its final, I guess I could put a final on here if I wanted to make it real nice on both of these. It also has some kind of rotational velocity, but its potential is 0 because it's reached the bottom and gravity can't do any more for you at that point. So I think we were supposed to solve for velocity, so we need to solve for v. So let's see what we've got now. So we've got that v right here. This part came from inserting the the rotational mass equivalent, which we call moment of inertia. So you look that up off your chart. It's 2/5 mass times the radius of the sphere squared for a solid ball. It's going to be different for every kind of object, whether you've got a hoop where it's just like a really thin edge thing, that's going to have a totally different inertia. So you got to look those up. All right, and then what did this come from? Where did this come from? Right here. I think that came from, and let me erase this guy. Alrighty. I think that came from this dude, because we know that velocity in a linear sense is velocity in an angular sense times the radius of the motion that you're moving through, the angle you're moving through. So in other words, angular velocity omega is linear velocity divided by radius, and I think they squared that, and that's what we've got here. The radius that thing's revolving is, of course, its own little spherical radius. Okay, so now we've got v in 2 spots, so we factor it out. So it looks like they factored it out. Oh, it looks like the masses are the same everywhere, so we can cancel these guys. I hate that big line. So annoying. Okay. And yeah, so the mass is canceled out, and then we've got what? We've got anything else cancel out? We've got GH left on the left. We've got half v squared, that's the final velocity, right? And then we've got another half times 2/5 of r squared, v squared, and that's over r squared. So I guess this part also cancels. So now we can just factor out that v squared on the right, and we get 1/2 plus, what is that, 2/10, so 1/5 equals GH. You can divide this part to the other side. Oh, I guess we can make a common denominator. What is a half and fifths? Oh, a common denominator is tenths. So that's 5/10 plus 2/10. That's 7/10. Okay, so we've got, in other words, GH equals v squared times 7/10. Divide your 7/10, so we've got 10/7 GH equals v squared, plus or minus on both sides, and you get your velocity. Just a quick comment that if we think about just a box going down the hill, so if we just had a box going down the hill up here, and it was going down the hill, and there was no friction applied, I think the box actually reaches. Okay, I'm back. So if you had that box just sliding down the hill, I think it actually reaches the bottom first. If you do the problem from earlier in the class, you get basically from applying a conservation of energy that, let me get a smaller pen, that potential at the top, mgh, equals kinetic at the bottom, 1/2 mv squared. So if you solve for v on that one, I think you end up getting the masses cancel again. I think you end up getting the square root of 2gh, which if you compare this answer to this answer down here, 10/7 is not quite as much as 2, so this velocity is smaller. So that's one result from this. Another result is when we did this problem, it's completely independent. This only depends on gravity and how high you started with. So the radius of the sphere does not matter. R is irrelevant on this problem, and so is the mass of the sphere. So the mass is also irrelevant. So I think that that's pretty crazy to find that relationship. But notice, it's not the same as it was if you were not a sphere. So even though it's independent of the actual size and mass of the sphere, the fact that it's rotating changes the answer and makes that final velocity smaller. Okay, let's go look at another problem. I think this time we're going to apply conservation of angular momentum. So this one says we've got an object rotating on a string, so I want to just get rid of this part up here. We're not going to be looking at that, okay? So we're looking down here. We've got an object rotating on a string. This guy pulls it down. So this guy is going to kind of move closer between 2 points in a system. So it says we pull it down. Here's how fast the object is rotating due to some external force that's being applied at the beginning. And it shrinks down to this much once we pull it through some. And it wants to know what's this final speed of the mass, and this looks like a final linear speed, so we might have to convert between angular and linear. I like this little approach. It says there's no net torque on the mass. If there's net torque on the mass, Angular momentum is not conserved, so you can't do this. There's no net torque on the mass, though, because this external force that's causing it to move in a circle, and it doesn't show what that is, but whatever, there's some kind of external thing going on here. That creates, it has no lever arm, so there's no torque on this object as it moves rotationally. There's no torque because there's no lever arm being created by this little guy right here. Okay? Yeah. Oh, excuse me, I'm thinking about that wrong. So this guy is the real force that's being pulled. Yes, it's moving in a circle, but as you do this, and that force is basically going like this up here, right? That force has no lever arm. This guy, I guess, does have a lever arm. So there we go. We're not going to focus on that too much, though. What we really want to do is apply conservation of angular momentum. So we've got that. Sometimes angular momentum is denoted by L. So the angular momentum at the beginning is equal to angular momentum at the end. You might want to remember that angular momentum is called L. Anyway, what angular momentum is just like linear momentum. Linear momentum, P, equals mass times velocity. So angular momentum, L, is equivalent to that. In rotational land, mass is inertia, and velocity is omega, angular velocity. So there we go. That's why they have that. Final equals initial if it's conserved. So it says our small mass is essentially a small particle whose moment of inertia is just basically a particle, so we're not having to apply one of those special formulas like for a hoop or something like you see in the other videos. So we're just doing straight up moment of inertia. Put that in on both sides. We want the final speed, so we're solving for this guy, so it looks like they solved for that guy. Then we remember that we have a little formula that says angular speed times r equals linear speed. That just came from arc length again. And so if I put little subscripts on here, because I want the final, or the second, linear velocity, that's what I need. So over here, how do you get final velocity? Well, I think what you basically have to do is multiply on both sides of the equation by r sub 2. So you multiply by both sides by r sub 2, okay? And then you have that on the left is now your linear velocity at the end. So V2 is now R2 omega 1, and then you have the ratio of the radiuses squared. Okay, so I think that some of that reduces. You get that this cancels this guy. And let's see, what else? And, oh yeah, we can substitute in here too. So this guy, you can also say is R1, excuse me, this guy is V1 divided by R1 from this same formula. So we get what? V1 R1 times R1 squared, and I canceled it out, so there's only one R2. So now I think this goes away with this, and we're left with V1 times R1 over R2, like they got right here. And you just plug those numbers in, because I think we knew all those numbers, and you get that the final velocity after this string has been pulled that much is 4 meters per second. Let's think. So it started out at 2.4. Okay, so I'm back again. What I was saying is our final answer of 4 meters per second, the fact that that is faster than the initial linear velocity of 2.4 meters per second, I think that definitely makes sense, because once we're down in here, I think we should basically be moving faster, at least in a tangential linear sense. Our linear velocity should be longer here than it was here. One good way to think about that in terms of a concept is if you consider a ballerina, and so I could draw a little ballerina, and when she has her arms extended, I don't think she's able to move too fast as she tries to spin. But if she wants to spin faster, one of the typical ballerina moves is to bring her arms in, and that increases. So up here, her tangential rotation speed as she goes around like this is going to be pretty small. But when you bring your arms in, just bringing your arms in, which is essentially what's happening as we pull the string on this little mass, just doing that is going to make her spin a lot faster, and this velocity vector is going to grow a whole bunch in terms of its magnitude. Okay? All right, let's look at one more angular momentum example, and this one is definitely cool. So this one says star collapse. It says astronomers often detect stars that are rotating extremely rapidly, known as neutron stars. Man, I just asked that at trivia the other night. Neutron stars are also the tiniest, densest variety of stars known to science. These stars are believed to form from the inner core of a large star that's collapsed. So depending on the size of stars, all kinds of things can happen. But if you have a certain variety of star, when it collapses, it forms a neutron star. So I don't know if our sun would actually do this. That's probably like bad information there, but it could. Let's suppose it can do this. So our sun has a radius of about this many kilometers, about, what is that, 70,000 kilometers. And it says this particular star, we're going to say, has about the radius of the sun, but is 2 times the mass of the sun. And it says this particular star rotates once every 10 days. That's pretty fast if you think about it, because of course the Earth is really, really small in comparison to the gigantic sun, and the Earth rotates once per every 24 hours. So, I mean, even though this is rotating once every 10 24-hour periods, it's so much bigger. So I think that's still going fairly fast. So it says, if it undergoes gravitational collapse and becomes a neutron star, which is super tiny, super dense, now it's only 10 kilometers after starting at 70,000, what would its rotational speed be? Okay, so it says the star is an external system, so there's no, is an isolated system. There's nothing outside acting on it. Of course, that's not completely true, but it's true well enough to apply conservation of angular momentum and get a decent answer, even if it's not exact. If we wanted to get to exact, we'd have to use general relativity, and our math skills would have to be about 7 years more advanced. So anyway, it says, from conservation of angular momentum, the angular momentum at the beginning is equal to the angular momentum at the end. And it says that, okay, so we write down the angular momentum as a product of inertia, mass, times omega, velocity. Inertia, mass, times omega, velocity. Okay, and what did they ask us to do? It says, what would its rotational speed be? I think they asked for the omega final, which they called omega 2. I don't like 2's, I don't know. But it's the final rotational speed is what they want. So you take this and you solve for final rotational speed, divide that inertia to the other side. Then you plug in the inertias. I think the sun is a rotating solid sphere, so this comes from you looking in your table or doing a calculus derivation, but pretty much we're going to look in our table in this class, unless we're going to take Physics C. And you're going to pull that out of your table. So for a rotating solid sphere, this is the inertia. How did they cancel the masses here? Well, if you remember, I think that we're not supposed to lose any mass. We're assuming that there's no mass lost, and that's actually how this process works. So when this giant star shrinks down to a neutron star, I mean, basically it would be so small that my point is way too big here. Its mass is not lost, so you can imagine the gravity coming off this sucker. It is like really trying to suck everything into it. This little neutron star is trying to pull everything into it. The Earth probably is going to get sucked in and die now. So yeah, that's definitely what would happen. So just keep that in mind. So no mass was lost. In other words, this is like a conservation of mass, so that's what allows us to cancel right here. And the 2/5, of course, also cancel. So we're left with just omega 1 times the ratio of the radii involved. Okay, and they gave us both radii involved, right? They said that it starts out really, really big and it goes to 10 kilometers. So I think the only thing we've got to do is figure out the beginning angular velocity, and once we have that beginning angular velocity, we should be set. So remember, what was it? Linear velocity equals radius times angular velocity. Okay, so what do we have there? And I don't, this is definitely a useful relationship. The frequency of something, how often it occurs, is equal to its rotational speed, omega, divided by 2 pi radians, because that's how many radians it rotates through every second. You don't have to do this with frequency, though. This is definitely a good equation. We'll come back to it in like chapter 11. But I think we can just get away with this. So at that spot, I think that we've got, let's see. Didn't they just give us that information? Let's see. Can we just use this right here? The book treated as a frequency, but I think that we can treat this as just omega. So I think that this says that omega 1 equals, so it should be like a number of radians per second. We don't have to do this in radians. They said what would its rotational speed be. We can give it to them in radians per second, or we could give it to them in revolutions per second. I think that's kind of up to us. So yeah, see, it looks like they came up with revolutions per second. I don't really care what they did, though. So let's see if we can turn that into an angular speed. So 1 revolution for every 10 days right now. Well, days is definitely not an SI unit, so I think we can convert that and say that 1 day is 24 hours times 60 minutes per every hour times 60 seconds per every minute. That'll convert into seconds, which is the SI unit for time. So I think that that is what they did down here. Can you see that part? That is converting basically omega into what? So now omega is going to be measured in revolutions per second. And then I think that probably makes more sense to us in terms of revolutions per second, how fast this little tiny, extremely dense neutron star is rotating per second. That makes a lot more sense to me in terms of revolutions per second than it would if I did radians. So that's why I think that they're leaving it in revolutions per second makes sense. So just do a ratio of the radii. Here it is. It's squared, of course, and here's our unit conversion. This is all just essentially omega. I just totally ignored what they did right here. I don't even care about any of this stuff. You could definitely do it that way, but it's easier to just go like this, okay? If we wanted to convert this to radians per second, we could, of course, just add another thing over here that says 1 revolution. Oh, I can't fit it. Let's do it over here. Okay, so here's this other part. So we'd say 1 revolution is 2 pi radians. And then we'd have radians per second, but I don't know. I like revolutions per second. What this says is that while at the beginning, the huge guy was rotating once or going around once in 10 days. Now it's going around, what is that, 6,000 times per second. So this crazy little neutron star dude is going to cause some super bad effects for everything else in the solar system and maybe even farther out. Because of his density, he's going to pull everything in, and he's moving super, super, super fast. So that also has gravitational effects if you study general relativity. All right, so hope you found this video useful.